The Electronics Alliance brings you another in a series of technical presentations to continually educate you in product design and manufacturing. Today's session is about 3D printing of multilayer PCBs and non-planar circuitry. We welcome Bob Diffin, Strategic Account Manager for AccuCode 3D. Anytime you need to find a qualified source for your design and manufacturing needs, contact the Electronics Alliance.
We're going to talk about 3D printing electronics, and Gary kind of was touching on really the whole focus and the way I see 3D printing and how it's, and kind of a lot of what Russell was talking about. Is just bringing things to market faster. I mean, right now through your traditional methods, if you were to order your first prototype PCB board, which, you know, let's hope it works, let's hope it lights up something, and then that gets sent off. And this is the feedback I get mostly from our customers that we're already working with. They're looking at anywhere from 3 to 4 weeks before they get that first iteration back. And then they make the changes, then they send it out again, another 3 to 4 weeks for that iteration to come back to see where their mistakes are. Finally, maybe they get lucky on the third one, it's 3 to 4 weeks before they get that one back and everything's working. So we're looking at almost 3 months of cycle time. Whereas when we're looking at additive manufacturing, when we're looking at this, let's say if it's a board of this type, board of this size and thickness, this is a 12-layer board, Jeremy?
Yes.
12-layer board, let's say 3.5 by 4 inches. 2 of these were made in 8 hours. So we can run this type of product, process it, and you could have it overnighted in a couple of days, of course, depending on where we are. Or if you have your own machine, then it's, you know, boom, you hit play. At the end of the day, come into work in the morning, it's ready to go. So that's the type of dynamic bandwidth that we're just shrinking to almost nothing, and that's really to me the main importance. You know, it's not waiting for a project to get completed. It's not getting diverted to another one. It's not getting 3 or 4 more piled on while you're waiting for your first one to get going. So it's just that ability to move things along, get things finished, get projects completed, because everybody likes to see something to fruition. I know I do. But, you know, and again, when you have these frustrations, even just asking for POs and ordering things, I mean, it's just that whole cycle when you look at the whole ball of wax of what you have to go through. And we understand it, because I get the feedback from the electrical engineers, and I say, tell me what your process is. And this is the consistent story I get every time we sit down and talk with, you know, virtually everybody that we've had meetings with. So, you know, that's just kind of the 30,000-foot view of my view on the 3D printed circuits, but we're going to get down into a little bit more of the technical stuff. I'm going to run a little video here.
So what you see here is really a meeting of printed electronics and 3D printing. So on the one hand, the item itself is printed, so you have a shape, a structure, and then within that you've got the electronic traces, the conductive traces rather, positioned so that obviously you can see here this is the beginnings of a thermometer. And one of the questions is, you know, how much of a product can I print? Well, so you can print that structural part, and you can start adding in that functionality as well. So you'll see these traces all the way through to the tip, and you know, the item being ready here for an LCD display to be added into that item. So this is really merging those two worlds of 3D and non-3D. This happens to be a sort of a planar circuit within an object, but you can, of course, also print the circuitry as a spiral, which we'll look at in a moment. So one of the shapes that's really exciting in the world of electronics is coils and spirals, and that, you know, that's the world of motors. It's beginning to look at things like capacitance, or in this case, an electromagnet. And what we're looking at here is 12 layers of coil that are built up. These layers are printed, they're very, very thin, because the printer is able to deposit very thin layers of material. And essentially what you get here is an entirely new way of making an electrically functional part, in this case a coil, which actually I can plug in. One thing that I want to show you is that it's not working as a magnet now when it isn't plugged in. But if we then connect that to a power source, as follows, give it a couple of seconds to warm up. That little magnet there is then something that you can pick up with the electromagnet, and it's fully functional as you'd expect it to be. Now, obviously, some people are very suspicious and think there's probably another magnet hidden inside there. So I will demonstrate what happens when you disconnect it, and you'll see that this is being driven by the electrical magnet rather than some other sneaky circus trickery. So what you see here is something you could essentially uniquely do with 3D printing. So we've printed in a geometric pattern here in order to enable this rigid polymer to have mechanical properties that you wouldn't normally be able to get out of rigid plastic. So it's maintaining that thickness of parts all the way through. A little bit as you might do with, say, CNCing into wood or metals to allow them to flex. So this is one way of bridging the gap between rigidity and flexibility in a part. So following on that theme of flexibility, so one way, as we just saw, is printing geometries into the polymer. And this part actually uses a slightly different technique where you might be able to make out the taper here in that polymer. So there's a mechanical strain relief, essentially. You go down from a thicker, rigid part of the board, which over here you can see is also the bit where you'd be able to, say, solder parts, or even in this case, into those cavities, you could embed the parts as well. And because of that strain relief going through, as the part gets thinner, it goes from being rigid to being flexible. And you can tune the amount of bend or flex you want to get in this part of the component by adjusting its thickness in your part design. So you can do both rigid and flexible. You can certainly use this, for example, in bend to fit type applications, where you might want things to fit into a smaller constrained space, and you can adjust the fit, not just in terms of size, but mechanical properties as well. So this little trinket is an example of what you could call an MID, like a molded interconnect device, along the lines of the way in which the antennas in most smartphones today are made, where you will need a topography to get the most out of your circuit in order, for example, with antennas to get that benefit of a three-dimensional antenna. Essentially what you're seeing here then is there's a right angle, which is the kind of shape in the conductor that you might associate with a traditional circuit, but you can also see, of course, that because we're printing, we can print in curves. If I turn the part over here, what you'll see as we do make that journey, first you can see the metal within the polymer, and you can obviously contour and shape that surface in such a way as to either have the metal exposed, which is really what you do with a traditional MID, where you'd be adding those conductive traces to the surface of a molded part. This particular approach, the dragonfly approach, enables you also to have those traces within the polymer, so you can envision things like a multi-layered MID device, which allows you to create objects that really wouldn't be manufacturable.
We're talking about the whole focus of Industry 4.0, Internet of Things, the IoT. It's all about changing the way we do things now. I mean, our biggest objection is, well, we've always done it this way. I mean, that's the thing that we hear and we go, because there's not much we can do about that except other than that, try to change your minds about that. And it's just a better way to shape things, a better way to design products, and again, bring them to market that much sooner. I'm thinking this is I do that one. Okay, so, and again, like Russell pointed out in his presentation, we'll have to, the production line before Henry Ford, but after today, you'll have a change of the same magnitude. So this is the actual machine on the right. And the typical PCB manufacturing process will include all of these components, all of these. You've probably seen one or two of these rooms before. And basically everything that is done in this room right here has now been condensed into one machine. And that's the whole focus of this of this machine and its technology of what it can do. Because we're looking at pretty close to, $1 million plus, maybe $2 million. I'm not 100% educated on the cost of all these components, but when it comes down to the ratio of cost to part, the Nano can definitely save you some money on that as well. So it's where additive meets electronics, and basically it's an additive manufacturing process. So what the machine uses, it uses two Konica Minolta inkjet print heads. One of the inkjet print heads puts down a dielectric material, which is like a rosin base, which is UV cured. The other inkjet print head puts down the conductive material, which is silver. And so those are the two products that we currently have now. Nano is always, as every manufacturer is always working on improving components and materials and things like that. But basically, that's what the process is now. And they're extremely precise. I mean, as far as laying down material thicknesses, the layer of the dielectric material can be as thin as like 25 microns. The conductive material is maybe 17 microns. And then you lay those down together. They're put through that curing process. And then you've got your PCB board of your design. And the ink viscosities, surface tension, goes over all these things. There is a whole design process. There's build design for the Gerber files, some minimum requirements and things like that the software needs to see. And so with those things, but these are just some of the basic properties of these components right now. So the silver nanoparticles, you can see how small they are.
Do you have the design guidelines posted somewhere on your website? So
You can have one emailed to you. And, yeah, and I believe they're posted on the Nano website, but we'll have Gary take care of that for you.
Perfect, thank you.
Yeah.
So how much post-processing do you have to do? Can you solder directly onto the silver printed solder pads?
Yes, you use a low temp soldering process, but this is as functional, and you can design or add whatever. So when you send us a standard Gerber file, and if there's any questions as far as fitting if you have a square peg to what we think is a round hole, we'll work with you and say, okay, what is this specific layer? What is this specific design? Can we do this and get you your same result?
Yeah. Let me put it this way: if any PCB fab shop you send the Gerber files to, you also instruct them, or they'll look at it and they'll do their tweaks for their processes.
Okay, fair enough.
So the aperturage and all the rest of the things for the plated through holes and all that. So when they do a quote, they'll go through and say, this is how much it is. Then there's a front end on there, and on the front end, that's where they're looking at all of it.
Yeah.
So from your engineer's perspective, just have them treat it like they would any other.
Yeah, see, it's just like this right here. There's a top annotation, a top solder mass. There's signals, the bottom solder mass, the via, the route. The route is the shape of the board. So all that would be basically like an 8-layer board right there, and that's the way the software looks to us before it goes into the machine. So that's the way we would interpret.
No, I'm saying, so there's a human being. There's a human being that would review all that stuff and say, hey,
Yeah,
this is
before
what
we
we
hit-
can do, and this is what we cannot do.
Before we hit go, we verify.
Right.
Yeah.
So
Nice.
in traditional board manufacturing, when you want to make a layer-to-layer connection, you have to do via. Since you're doing the additive process, I would imagine in theory you could actually just print the silver basically as a small column between the layers, and not have to do
That's pretty much how
real
it works.
large vias.
And we
right?
do it in 17 micron layers. So that's hence why it takes a little bit of time to make these things. Even though it took only 8 hours to make 2 of those boards, it's still a process.
Right. But that means you could actually do something in the 3D printing that you can't do in the standard board.
Right.
Instead of having a view, you could literally have just
Right. You can actually change the
column.
shape of the board. It
Yeah.
does not have to be flat.
Yeah.
Tony hit on it exactly right. Okay, the first thing I wanted to do is get a product that was interchangeable, so that your engineers already have this all built up,
Right.
all of the vias and all that. But you're taking it to the next level and says, hey, what things can I do with additive that you can't do with the other technologies?
Right.
And you could make, round conductors, and you can make spaghetti and There's a lot of things you can do in the software.
That's what, like in the video,
Yeah.
it was showing that curved shape, so it can print curved connectivity, it can, but this is called our switch software. And so here's the design of the product with its identified layers, and this is the end product, where you can see the connections we're solving.
So one of the things that you mentioned in the beginning is, one of the benefits of this is I can send it to you guys or by my own, have it done very quickly. How does it compare though in terms of cost? If I'm gonna send a board out to a place and I'm gonna pay $3,000 or whatever in tooling to get 5 or 10 made, is this gonna be more expensive, is it gonna be less expensive?
We're pretty competitive. We might, it
it's not
depends
that
on the
I'm spending
board
more
design,
money
and it
to-
depends on the amount of time it takes to print the board.
Sure.
So it's all time and materials.
Okay.
So based on time and materials, that's kind of what we go off of as far as quoting out, individual boards. But as far as the cost, if you had your own machine, it's definitely a savings.
So it's not like I have to pay more, but I'm making enough time, it's really a comparable price, roughly?
Yeah.
Okay, great.
We don't want to, part of our goal is to, we realize there's a value in speed, but we don't want to price ourselves out of the market either. I mean, if you can get a board done for $200, well, we're not going to charge $1,000 for it, just because we can get it to you tomorrow.
Yeah.
Yeah. So, that's our thought process on pricing and stuff. But we have a whole formula that factors in, time, materials, setup stuff. And it may cost, let's say, like we just did a quote for one customer, it cost $700 for the initial setup. But to print each additional board, it was only $25. So you could get 10 boards, basically for $1,000. So $100, which is pretty reasonable.
Yeah.
What size?
That was 2 by 2, I think. Or what size was it, Jeremy? Do you remember?
2 by 2.
2 by 2. Yeah. So again, there's not a limitation in the board layers. There is a limitation on the board height, which currently is 3.5 millimeters. So however many layers you can squeeze into those, that height limit, that's what the machine will do.
That's the thing you can get?
3.5 millimeter thick, that's the maximum thickness, yeah. And it's just for accuracy purposes right now. I mean, they could have and it's also the gantry travel, things like that. It's part of it's the way the machine is engineered. So to provide the accuracy on the Z, they've limited it to 3.5 millimeters for now. I mean, with height development coming in the future, in the very near future. And this is kind of going back to your point, Tom, is it Tom? Or?
Tony.
Tony, okay, Tony. Yeah, so as far as building the vias and the way that you design things, it's not just a typical PCB design. It's not just flat. So you can add that third dimension with additive manufacturing to create this other new design feasibilities. So, and the vias can be blind, buried in the pad. The line trace widths are 4 mil or 100 microns. Line traces 5 mil, 125 microns. So it gives you the opportunity for new breakout options, new ideas. It kind of forces it's all up to you. How much of this technology do you want to take advantage of? Do I want to maybe save a whole manufacturing process because now I can print a 3D layer via and not have to include that in a manufacturing process because now it's it's got a right angle to it and it's going up. So that's the benefit again of this type of technology because you're just not going to get that with typical PCB manufacturing.
That's fascinating. I mean, it almost does away, well, again, if you don't want to maintain compatibility, it almost does away with the concept of a layer. There's no layer anymore, it's just a 3D blob and you can
It's
go
wherever you want that
that
connectivity to go and it's where those vias are going to go.
Yeah.
And that's what you're controlling. Thanks for coming, Lee.
Thank you.
All right. So, and like I was saying before, there's no known layer count, but it is the layer height that we're controlled by. And that's just an example of that 12-layer board. I think I already passed around that other one that I talked about before. Yeah. And so here's a whole circuit design to finished product in 48 hours. That includes the, the soldering. It includes, getting all the components put on it. What does anybody get to go through that fast a process now? Does anybody being able to generate that type of turnaround with their designs and ideas as far as getting it from start to finish? I mean, that's pretty amazing. So it goes through, you can put it through all your standard testings, like I was talking about before, as far as the soldering process goes, we recommend the low temp soldering process. There's a whole design guide and process for that that we spec out for you. As far as taking x-rays, it'll show up as a bed of nails, all of these things. Whatever you're doing now, these boards will have the capacity to, it's got reflow compatibility. So all of these things that you're doing now, you're going to be able to replicate with these boards. And of course, it can do more than just multi-layer PCBs. It can do these types of electronic components, not typically seen in your PCB shops. So it's really the capabilities are endless, and it can really go to whatever direction that you're willing to take it. And yeah, we can do other designs. We can talk about these other designs. We talked about the coil. We talked about the RF antennas. This is an example of this is a board antenna that was printed by Harris Electronics. We can say the word Harris Electronics because they have released a white paper on that antenna design and several other papers that they've written on as far as the electronics and components they've made. They've told Nano that on their next Mars shot that there's probably going to be about a half a dozen of the Nano boards on that ship. But this is, again, this is going through your options. These are, so it's not just, we're just not filtered down to just making PCB boards. If you're in, you've got several other components that make up your electronic device, well then that's what we're going to be able to accomplish on the sheet. This kind of goes to what you were talking about earlier, about as far as the vias and where that you want to be able to take that design to. So here's your vias. You can see how that connectivity is. So it just builds those, like you were saying earlier, Tony, it builds those columns of connectivity, and that's what it gets to your varying the capacitor thickness and the thickness of depth. And this is an example of that. This is that 3D design of that sample that you saw in the video earlier, where it showed that connectivity. It showed that it does work when it's charged up. I thought he went a little over the top as far as proving whether it did or not. But yeah, this is all able to design with software. They've also got a hard link to SolidWorks. So if you're using SolidWorks for your electrical engineering design, there is a link to export those files that'll just be read by the switch software just right away. And again, talking to those flexible rigid circuits, this is a great example of seeing how it's much thinner here, and you can actually fold those three edges up, and then connect it in one part. It's all up to you to decide what you want to do with the technology. It's up to us to be able to provide you that solution. When you do, to me, when a manufacturer does something, they want to do what they do right and do it well before they start moving on to the next level. And this is what they've already got the proof of concept. They've already got the machines that'll do what they need to do well right now. And this kind of talks to that Harris antenna, where it had the through holes for the connectivity. Substrate stiffener was 70 mil. So layers are 2 mil, substrate 20 mil. So all of that is that's just basically how it's broken down in the switch software. And that's what the switch software sees, and that's what you get as far as the end product. And of course, you can build multiple of those on the build sheet.